everyone. So yeah, this is a session on how Coinbase builds out its blockchain infrastructure. Um, just a little bit about me. I've been at Coinbase for 2.5 years now. I've done a lot of stuff. Worked on the infrastructure and security engineering problems. Um, I was like a founding engineer on the Coinbase custody product that we launched about this time last year. We kicked off this time last year. And so I've done a lot of like crypto storage stuff at Coinbase. So we're going to talk about, I guess, 3 high-level topics today. First, I'm going to talk about Coinbase, some particular constraints of our business, and sort of how that impacts our infrastructure. We're also going to do a little bit of a deep dive into our infrastructure, some of the choices we made around that, revolving around security and sort of the ability to move quickly the ability to move quickly. Next, we're gonna talk about blockchain networks. I assume a lot of you know a little bit about blockchains, but I'm gonna give you like just a brief overview of them for those of you in the crowd who don't know much about blockchains. And then lastly, we're gonna talk about Snapchain, which is a project I worked on over the past little while to seamlessly and easily deploy blockchain nodes within our infrastructure. Cool, so first talking about Coinbase. Coinbase is a place to buy and sell digital currency. We like to call ourselves the easiest and most trusted place to buy, sell, and manage your digital currency. So for this talk, I'm gonna talk about, I think the most trusted component of that is really important. Most trusted means a couple things from my perspective, or the work I do at Coinbase. It means we need to be reliable. We need our services to be up when people want to be trading. It also means that we need to have security at mind in everything we do. So we need to treat people's funds incredibly carefully, and we can never really let any severe or major incident happen. Coinbase wasn't always a place where you could interact with a lot of different cryptocurrencies, though. Originally, it was just a place to buy, sell, and hold Bitcoin. Since that time, since like the early days, we've added quite a few more currencies. So now we have Bitcoin Cash, we have Ethereum, we have Ethereum Classic, Litecoin, 0x, and a few more. And we're adding these all the time now. So we're sort of increasing the rate of adding assets. And if I was to give this talk at reInvent next year, I think this slide would be like chock full of all sorts of different assets. So this is like a very critical part about our blockchain infrastructure. Is we have to be thinking about scaling the number of assets in mind whenever we're thinking about doing a major infrastructure project. We can't be building super specific tooling to any one blockchain, and rather we need to take this approach that's generic across as many blockchains as possible. And so what was once a place to buy, sell, and hold Bitcoin has now become a place to buy, sell, and hold crypto more broadly. But Coinbase has also expanded on the number of use cases and the number of different ways to interact with these different cryptocurrency networks. So we now have Coinbase, we have Coinbase Commerce, which is like a merchant tool platform. We have Prime and Pro, which are high-frequency trading products. We have Coinbase Custody, which is an institutional storage product. We also have Coinbase Wallet, which is a user-controlled wallet. Also, earlier this year, we acquired Paradex, which is a peer-to-peer exchange. And then we also have Earn.com. So that's just to say that now we've become a place to buy, sell, and do a whole lot of other things with crypto. The number of use cases has expanded dramatically, and with that, the type of infrastructure we need to enable those use cases has changed pretty significantly. Additionally, we've grown substantially, I think, in the traditional way people think about a company growing. So this is our request volume through April 2017, and then Cryptomania happened, and things just went a little bonkers. So we're scaling kind of in many different ways. We're scaling the amount of traffic, so just the traditional way you'd think about scaling a web application. That's request to the API, that's request to your database, that's things like that. But we're also scaling the number of business units. and with each business unit might come different ways to integrate and interact with the blockchain, we're also scaling the total number of blockchain networks that we support. And so from my perspective, as somebody who thinks about blockchain infrastructure at Coinbase, we've always wanted to build secure and scalable infrastructure. But now we've really added on this additional mandate of thinking about building blockchain-agnostic infrastructure. So that's building infrastructure that can be as generic as possible across as many different chains as we can. And that just means that we can more easily spin up new chains without having to do anything super custom per chain, as much as possible. Now I'm going to talk a bit about infrastructure at Coinbase and some of the kind of like tenets that we've implemented within our infrastructure. So the first one, yeah, that's a mission control center. The first one is that our infrastructure is immutable. And what I mean by immutable is that any configuration change requires a redeploy. This ensures that all configuration changes are tracked in source control, and also ensures that we're always in a deployable state. So we can never get to a point where somebody hops on a box, mucks around, does something, downloads a few dependencies, and we don't know exactly what happens. Instead, everything is immutable, and so anytime we change something, we entirely tear down and rebuild the application. Kind of together with this idea of immutability, Coinbase's infrastructure is ephemeral. So every server in our infrastructure lives for less than 30 days. In practice, this isn't always the case, but it's something that we strive to do. It's like one of the core KPIs of the infrastructure team. This is a huge security win. This means that if any vulnerabilities were to come out, we're constantly redeploying these servers, tearing down the old ones, and pulling in the updated packages that might have a vulnerability. It also means that if anybody were to ever gain persistence, like an attacker were to gain persistence in our network, we'd constantly be pulling the rug out from under them. So we'd be tearing down the box that someone might have, and it'd be incredibly difficult to maintain persistence in our cloud. More on the human element of the infrastructure team, we've implemented this idea of consensus. So within Coinbase, consensus really means that no one person can perform sensitive actions individually, but any sufficiently large group of people can do anything, any scary action together. And this is a critical idea, and it's carried through like all throughout like our tooling across Coinbase. Typically, the number of people required to perform an action is like proportional to the sensitivity of that action. And lastly, as much as possible, we try and make our tooling and automation self-service. So both consensus tooling and self-service requires a heavy dose of automation. So we kind of combine consensus and self-service together into one application where we can enable engineers to not have to work directly with the DevOps engineers to do things they need. And instead, we build a tooling that allows them to do what they need to do. So with consensus and with self-service tooling, it means that all application deployments are completely engineer managed. They're not really managed by the DevOps team or the infrastructure team. Instead, deploys and rollbacks are handled by the people who know those applications the best, the engineers who built them. So instead of having a DevOps engineer who spins up an application, performs a deploy, and doesn't really know what a particular log line means or doesn't know the expected number of 500s an application is supposed to throw, we have the people who actually know and actually wrote those applications, the experts in those applications, shepherd the deploys. Cool. So that's just like a little bit on Coinbase and our infrastructure. Now I want to talk a bit about blockchain networks. And I apologize, this might be a little redundant if you all have seen or know a bit about blockchain networks. Actually, how many of you know much about blockchains? Like how many of you have seen a talk like this before on blockchains? Okay, a decent number. So a blockchain is just a linked list of blocks, where each block contains modifications to the global state. Now, if you're a crypto nerd, you might know that different blockchains are coming out now that actually don't implement linked lists, A lot of the fancy cutting-edge projects are using DAGs, or directed acyclic graphs, instead of a linked list of blocks. I think it's easiest for us to sort of illustrate just a linked list here, so I'm going to implement that. Also, I want to call out that I'm saying global state here. I'm not saying account balances, which you might use if you were talking about the Bitcoin network specifically. I'm not saying smart contract state, which you might use if you were talking about the Ethereum blockchain specifically. Instead, I'm saying just global state. This is any blockchain, and then any blockchain might have different types of state, or might have very different use cases. So I'm trying to keep this as generic as possible, and that'll just be a theme throughout this presentation. I'm going to talk about global state. Okay, so we have 4 blocks here, and this is a chain of blocks. Each one of these crazy-looking numbers is like the block header, and each subsequent block references the previous block. And so, as a new block comes into the system, and it contains a reference to its previous block. So in this way, we're just constantly amending this chain. The chain is constantly growing. The amount of state involved is constantly growing. Also, blockchain networks are decentralized peer-to-peer systems. So there's no central authority that's propagating these state updates throughout the network. Rather, the blockchain nodes validate, detect, and relay these state updates throughout the network. So from Coinbase's perspective, these nodes are our eyes and ears into this network. Whenever somebody wants to send funds into Coinbase, they log into their app, we show them a deposit address, they use a wallet they might control and send their funds, and we can actually detect that they did in fact send those funds to an address that we control by querying these nodes. So we're pinging these nodes and saying, did this transaction actually occur? Yes. In the event that it did, we can credit their account balance. Similarly, on the other side, if somebody wants to send funds out of Coinbase, we create a transaction, sign that transaction, and broadcast it through one of these nodes. And then we query the node to see, did the transaction actually propagate through the network? Did it confirm? And once we're convinced that it actually did confirm, we can decrement their account balance, and in that way we can have a smooth running application. So these nodes are really critical to our core business operations. If we don't have nodes running, we can't really integrate or interact with the blockchain networks in any way. We need these nodes to be reliable. And also, as I was mentioning earlier on, we take security incredibly seriously. And so we want to be able to frequently and rapidly redeploy these nodes into the infrastructure, into this ephemeral and immutable infrastructure. So before digging into what Snapchain is and how we've sort of improved upon the traditional way of deploying a blockchain node on AWS specifically, I want to take a second to just talk about what a basic or sort of simple deployment of a node would look like on AWS. So we'll start off, we have just a basic EC2 instance, and we'll assume that this instance has our node binary on it. It has a copy of Bitcoin D or a copy of Geth or Parity if you're in Ethereum. Once this node binary comes online, it'll immediately peer out to the network. It'll find other nodes online that have copies of this blockchain. Now, each node actually retains a full copy of this blockchain. And so assuming that these other nodes are up to date, our node will start requesting new blocks from these nodes. So we'll pull one block down from the network, then we'll pull another block down from the network, and eventually we'll get fully in sync. We'll grab all the blocks from the network and be fully in sync. And at that point, we can use this node successfully. We can broadcast transactions through it. We can query it for some account balances and the like. I just want to take a second to say that this is quite a lot of data. So this is an image of a disk usage of one of our Geth nodes that I took, and it's actually a couple months old now. At this time, we had 952 gigs on disk, and now it's like quite a lot more than that. So it is quite a lot of data. But if you guys are DBAs or you've worked with databases before, 952 gigs it's a lot of data, but it's not a crazy amount of data. We definitely have database technology that can handle that. The issue here is that we have concerns with network reliability. So when our new node comes up, we have to pull down the entire blockchain from the network. And these networks aren't necessarily the most reliable. Pulling 952 gigs over the internet already would take a while, but because this is from a distributed peer-to-peer network, it can actually be pretty difficult and take a long time. And the network reliability is really an issue because these are open source clients that are developed over a pretty short period of time. There's odd things like economic incentives sometimes, really directly monetizable economic incentives for people to disrupt the network. Unlike traditional, I think, DDoS attacks, crypto networks are particularly susceptible to this. And we've also had to contend with hypergrowth in the form of CryptoKitties. If you're familiar with CryptoKitties, this is in many respects the bane of my existence, because CryptoKitties has introduced just a ton more state to the Ethereum blockchain than there otherwise would be. So network reliability is a real concern. So all of this together just says that node management is actually a pretty hard problem. We have all sorts of different implementations. In the case of Ethereum, we have Geth and Parity. Coinbase wants to run more than one implementation if possible. There are clients that are being developed by teams of developers, so they're constantly being improved upon. New versions are coming out all the time. Sometimes vulnerabilities come out, and we want to be able to redeploy away from a known vulnerability as quickly as possible. Typically, there's multiple chains to support, so there's typically a mainnet and a testnet. We want to support a testnet so that we can actively develop against it and improve our applications. From Coinbase's perspective, we have a number of different business units that each support and require different configurations of these nodes. And this is a ton of state being propagated through sometimes pretty unreliable networks. Okay, so let's recap these constraints quickly. We want frequent and rapid deploys. Coinbase is a very security-conscious company. We want to be able to respond to any incident quickly. If a vulnerability comes out in a network, we want to be able to react to that quickly and redeploy these nodes. But these are stateful applications, and there's quite a lot of state at play. We're also contending with this immutable and ephemeral infrastructure. So this is where Snapchain comes in. At a very high level, Snapchain is a tool to blue-green deploy blockchain nodes. There are a couple design constraints I want to talk about when we're thinking about Snapchain. The first is that we wanted to minimize the blockchain-specific code and infrastructure as much as possible. We didn't want to build this. We didn't want to build a new solution per chain we had to add. And instead, we wanted to build a solution that would support as many chains out the box as possible. We wanted it to be flexible and apply to many different chains. Unfortunately, there's a point where we can't be as super generic. There's a point where we have to get specific. And we've carved out this area, node health, and said node health is something that we're going to have to implement. We're going to have to consider on a chain-by-chain basis. So if you're familiar with automating deployments in AWS, you frequently implement a health check function on your application to ensure that if your application can no longer talk to your DB or your cache, you can tear it down, replace it with another instance, and everything's happy. In the case of Snapchain, we also implement a node health check. And typically this looks like we look at the time of the last synced block and compare that with right now. And if that grows too far, we know that we're pretty out of sync with the network, and we know that we want to actually tear down one of these nodes and continue. But different blockchains produce blocks at very different rates. So in the case of Bitcoin, blocks are produced on average every 10 minutes. In Ethereum, blocks are produced on average every 15 seconds. So these are like pretty different rates of block production. So we have to treat this pretty differently in the case of Bitcoin or in the case of Ethereum or any other. Also, these networks might require different peers. So additionally, 10 minutes in the case of Bitcoin or 15 seconds in the case of Ethereum, it's just an expectation. Blocks don't actually occur on a predictable cadence. It's a probabilistic thing. And so there can be moments where blocks don't get produced in Bitcoin for 20, 30 minutes. We don't want to have to, in the event that there's like a network disruption or blocks haven't been produced for 30 minutes, I don't want all my nodes to fall out of rotation and me get paged in the middle of the night. And this has happened a number of times. So we actually fall back. We look at the time of the last synced block, compare it with now. If it gets too far, we know we're probably out of sync with the network. We know it's probably time to redeploy this node, tear it down, but maybe not. Maybe the network's just having difficulty. So we're going to actually reach out to other third-party block explorers, see what their state of the network is. And if it's different from ours, we will know, actually, yeah, we are unhealthy. But if they also haven't seen a block for 30 minutes, it's just likely that the network is experiencing some difficulty and hasn't produced a block in a period of time. The next design constraint of Snapchain was that we wanted to minimize the time to sync from network. So we wanted to minimize the total amount of time and the total amount of state that we actually had to pull down from the network whenever a new node came online. So with that goal in mind, we realized we needed to separate the blockchain data production from the data consumption. We needed one way to produce blockchain data, and then in a completely separate setting, be able to consume that data. From that, we sort of arrived at two configurations for Snapchain. What we call the snapshot configurations. Those are nodes that we spin up, we sync the chain, we take a snapshot, and are constantly producing this blockchain state. And on the other hand, we have long-lived configurations, which consume the state produced by snapshot nodes. I'm going to step through these individually, but first I'm going to dig into the snapshot configurations. So again, we're going to start with an EC2 instance. In the case of Snapchain, we'll always have two containers on this box, the node container itself and then an API or a control container. We'll assume that we're syncing from scratch in this case. So we're going to create an EBS volume on the fly. We're going to attach it to this instance. We're going to create a file system on it. We're going to mount that. And then we're just going to turn the node on. So this is looking fairly similar to the previous blockchain deployment we talked about. We're going to find peers in the network. And we're going to start syncing blocks just as before. So we'll sync 1, we'll sync 2. We'll get in sync with the rest of the chain. We'll wait to see if other health checks have passed that we've defined on a chain-by-chain basis. And once they actually have fully passed health checks, we're just going to turn this node off. We're going to flush everything to disk, and we're just going to take a snapshot. Here's a snapshot that occurred at 1 p.m. Next, we're just going to turn the node back on. Now, keep in mind that even though our node was offline, the network itself continued to run, so blocks were continually produced. So our node now is probably missing a block or two, and it's going to reach out to the peers it had before and sync down the missing blocks. Again, once it gets healthy, we're going to stop the node, flush everything to disk, and take another snapshot. And we literally just repeat this process forever. We start, we wait for the node to get healthy, we stop the node, we take a snapshot, over and over and over and over. And in this way, we produce consistent, trusted snapshots on a regular cadence. I want to take a second here to talk about AWS tags. So we're producing these snapshots super regularly. And we're supporting all sorts of different configurations for all sorts of different business units within Coinbase. The way we manage these and know which snapshot refers to which protocol is using just AWS tags. So typically we tag each snapshot with 4 different tags. We'll have the implementation, the network, the version, and the specialization. So in this case, this is a parity node. Parity, again, is an implementation of the Ethereum blockchain running on the Ropsten test network. It's running version 2.0.6 of this node, and it's just a default configuration. There's nothing super fancy about how we've configured this snapshot. But doing this allows us to know exactly what is held on each snapshot. And tags are super powerful. If you're not using tags all throughout your infrastructure, I highly recommend you look at them. Okay, so we've talked about how we produce snapshots regularly and how we're producing this consistent stream of snapshots from these chains. Now I want to talk about consuming these. So again, we're starting out with an EC2 instance. We're going to create 2 containers on this box, the node and the control container. This time, though, we actually don't have the data in place. We're going to want to base this chain, this node bind. We want to start this node off of like a known predictable point in time. We don't have the data in place yet. So we're going to look out and we're going to see what snapshots are actually available to us. So here we have a snapshot from 1 p.m. that's running against chain A. We have a snapshot that was taken at 2 p.m. against chain A. And we have a snapshot from 2 p.m. on chain B. We'll assume this is chain A. So the most recent snapshot here is the one in the middle, the 2 p.m. from chain A. So we'll take that snapshot. We'll turn it into a volume on the fly. We'll mount it on our box. And only at that point, only when the data is actually in place, then we turn the node on. Again, just as before, we'll find peers. But this time, we have a full copy of the blockchain. So we don't really have to sync anything from the network. It's pretty much fully ready to go, and we can immediately start serving requests. This is huge for us in terms of speed and safety. The snapshots themselves can actually take a long time. If you've used EBS before, you know EBS snapshots, like the actual time from when the API call returns to when the snapshot is ready to be turned into another volume can take a long time. However, restoring snapshots is really, really quick. It's a very quick operation. And so snapshot operations actually don't affect our live nodes. We have live nodes running over here, and entirely isolated, we have snapshot nodes running that requests aren't going through, and the snapshot nodes actually won't affect user data at all. I want to talk a little bit about network load balancers, or NLBs. If you're not familiar, network load balancers are a new type of load balancer in AWS. It's not super new, I guess, but it's new-ish. And network load balancers, along with application load balancers, replace the traditional or classic Elastic load balancers. NLBs, though, are layer 4 load balancers, so they're basically only like TCP load balancing. As I mentioned before, we're running an ephemeral infrastructure, and that means that we really don't have static IPs anywhere throughout our infrastructure. NLBs offer static IPs, and that's a really, really nice thing. Like other load balancers in AWS, they scale to meet our demand, which is a huge thing for us. It also gives us an opportunity or a target to do these blue-green deploys behind. So let's assume that we have a client application that's managed and maintained by one of our Coinbase engineers, talking through an NLB to one of these long-lived Snapchain nodes. NLBs actually have an interesting property called cross-zone load balancing. Most of the time, I think you'd want to run cross-zone load balancing on. Blockchain nodes, however, are a different application, I think, than you'd typically put behind an NLB. And so we actually run cross-zone load balancing off. And what cross-zone load balancing does is it says if a request comes in from AZ1 and there's a node actually running behind the NLB from AZ3, the request can go through AZ1 and into AZ3. If you disable cross-zone load balancing, you no longer get that. You get an instance of each NLB in each AZ. And in our case, we just put a single node behind each instance of this NLB. So in this way, we get one static IP per one node in one AZ, but we can do a blue-green deploy behind all of this. It's very convenient. So I mentioned previously that blockchain nodes are likely different from an application you typically put behind an NLB. These are stateful applications, and so these applications can actually diverge for short periods of time because they're pulling blocks down independently from one another. So we might have one node that has one chain tip and another node that for a brief period of time has a slightly different chain tip. If we had both of these nodes behind the same instance of the NLB, they might be returning different data from one another. So in this setup, we actually get around that problem, and it's just a very kind of a novel way to use NLBs, I think. So NLBs also offer us a target to do blue-green deploys behind. It's not that different from a standard blue-green deploy if you're familiar with it, but I'm going to walk through it here anyways for those of you who aren't familiar with it. So we'll assume we have a node running that's running version 1.0.0, and maybe a security vulnerability comes out with this node, or the developers have just pushed some new features and a new version drops. We want to redeploy this node quickly, so we spin it up, and we took a snapshot recently, but not that recently, maybe it was 20 minutes ago, so we still have to sync a few blocks from the network. So we wait for this node to get fully in sync. Sync down one block, sync down another block. And as soon as we've passed the health checks that are likely specific to this node, we're going to do a cutover. And now the NLB is going to be serving traffic only to this version 1.10 node. Again, we're running an ephemeral infrastructure here, so this node on the bottom, that just dies. We just take it away. And that's not concerning to us because we have these predictable snapshots. We can always roll back to a point in time if we need to. So version upgrades are super slick. You might think here, if this is the first time you're running a new version 1.1.0, there's not really a snapshot for that version yet. So how do you handle that? This is where we've built a snapshot selection engine to just kind of intelligently select the right snapshot based on a particular node's version. So it's going to say, I don't have a snapshot for this version yet, but I do have one that's close enough. I'm going to select that one and roll onto it. Also, as I mentioned, rollbacks are very painless. We're not concerned about rolling back because we have consistent and predictable snapshots to roll back to. So we've talked a lot about the automation in Coinbase's infrastructure broadly. We've talked a lot about the specific blockchain automation that we've developed. And together, these two things has made the process of deploying these blockchain nodes globally incredibly easy. This is like a pretty seamless process to take from just US East 1 all the way around the world. I want to talk for a second about a cool Lambda function we developed to clean everything up. So we're producing all sorts of different snapshots regularly. So we're actually producing a ton of different snapshots. And we, at various points, took down the entire staging environment of Coinbase because we exhausted our AWS account limits for EBS snapshots. So at some point, we realized we needed to have a way to tear down or remove snapshots that weren't really necessary anymore. And so we implemented this with the Lambda function. And I like it. It's just kind of an elegant solution. So we just say, we'll keep every snapshot we produce for 3 days, so we can roll back to a very granular point in time for 3 days. And then after that, we're just going to keep one date chain protocol tuple for 50 days. So after 3 days, we have like a less granular way, but we can still roll back for 50 days. And then after that, we just hard delete everything. So we've done a lot with Snapchain. There's a lot more we can do with Snapchain. So I briefly want to talk about what's in store for the future. First, I would love to open source it. I'd hope to open source it prior to reInvent this year, but things happen, and we didn't get around to it. I would like to open source it so other people can just use this and spin up their own nodes pretty easily. along with that, or in tandem with open sourcing it, I'd like to create a dedicated AWS account that Coinbase can actually be sharing EBS snapshots from. If you're not familiar, EBS has a functionality where you can share EBS snapshots across different AWS accounts. But you can also share them publicly, so you can just make a snapshot publicly available and anyone can grab it. So I'd like to create a dedicated AWS account where we can share snapshots or checkpoints of the blockchain so that anybody then can grab that checkpoint, know that it was produced by Coinbase and is likely a reliable source, and stand up their own nodes pretty easily. Also, we need to do a lot of abstractions on top of this node management. So it's becoming fairly cumbersome. The configuration for these nodes is actually pretty similar. And so we need kind of a better user interface to handle the assortment and wide array of new nodes that we're going to have in the coming months and years. So again, Coinbase is a super security conscious company. We want a way to spin up and tear down nodes easily. We built Snapchain to solve that problem specifically. And it is running in production now and is pretty cool. So thank you all. I'm Jack Carney. You can email me at jack@coinbase.com. We're going to do a Q&A session now, and then I'll just be hanging out here after for a while if you want to come talk to me about any of this.
First question is, can you talk about your testing protocol and deployment pipeline?
Yeah, sure. Testing protocol, so testing is really hard. Blockchains are, again, they're stateful applications, and even the test nets are pretty beefy test nets. So we rely heavily on unit tests where we can. And frankly, I think we haven't really gotten the testing protocol down pat for Snapchain. It's taken a lot of manual work to get it to where it is now. You can sync stuff locally and develop against it, so that's nice. Our deployment pipeline it's a custom application that we wrote. It's, other Coinbase engineers have actually given presentations on it, so I encourage you to look up those presentations. It's called CodeFlow, and it does blue-green deployments of auto-scaling groups really, really well. So we just use that for Snapchain also.
So you have 14 questions, so to speed it up, I'm going to let you just pick them off the top. And then
okay, cool. I'm not sure about this one. I don't know what that is. Yeah, okay, so the top question's great. Can you talk about what the hardest lessons learned have been with your immutable infrastructure approach and what you've done in your tooling to adapt? So this is really hard. I think first and foremost, we've just put a lot of time and energy into the tooling itself, into CodeFlow specifically. One of the hardest things about running an immutable infrastructure like this is nobody basically, no engineer in the entire company can SSH onto anything, or pretty much no engineer has elevated permissions in AWS. And so we've to just do basic development in Coinbase, we've had to produce tooling that works really, really well. Without that tooling in place, we couldn't ship code. And so, yeah, we have several dedicated engineers who are working on this tooling specifically, this deployment pipeline, to make it as easy as possible. I could probably give a whole talk on IAM permissions and how we handle that, how we sort of section that off and give different teams different levels of permissions, basically only based on their operational needs. Oh, how does Coinbase handle hard forks? There's been a lot of lessons learned, and there's a lot to this question also. Typically, we pretty much if we know that a hard fork's coming, we turn off buy, sell, send, receive. We turn off our integrations with these nodes prior to the hard fork occurring. We take snapshots of everything, and then after the hard fork has occurred and we know that both chains have stabilized, then we can come back online. Why use time metric for block synchronization instead of using canonical node client check right away? So you can use the node check, you can have a node, each node might implement that differently, and we basically layer this on top of any health check that the node itself might offer, so we can sort of have a more granular understanding of how our node is doing. Let's see here. if you want to use blockchain with rollback in time functionality, why not using a standard DB? So these blockchain nodes actually they have their own database. So in Bitcoin's case, it's, I think, level DB under the hood, but it's running alongside the node is like running against a level DB instance that's actually on disk. And so we can't necessarily use like an RDS instance or a traditional database. We're just sort of like using the node and allowing the node to do as much as possible without having to like write a ton of custom code per node. So we want to, again, utilize the node's functionality and not have to try and minimize the amount of custom work we have to do per chain. Coinbase, yes, we have open sourced other tooling. The infrastructure team has shipped this product called GeoEngineer, which is a Ruby wrapper around Terraform that we use to codify our entire infrastructure. There have been talks that my coworkers have given on GeoEngineer specifically. It's a great tool. It lets us do a lot of interesting stuff that Terraform out of the gate doesn't do. And one really nice thing about GeoEngineer is that it's Ruby based, and Coinbase is mostly a Ruby shop. So pretty much all of our engineers know Ruby and can actually contribute to GeoEngineer and the applications that sit on top of GeoEngineer. For your EC2s, you use custom AMIs with pre-installed binaries and dependencies. So we do use custom AMIs. We ship a baseline custom AMI. We call it Minion. And it's sort of based off CoreOS, but it's a little different. Everything is Dockerized in Coinbase. We're not actually baking the node binaries into the AMI itself. Rather, the node comes online, the AMI spins up an instance, and then it pulls down whatever containers it needs before actually starting up. Sort of talked about this one already. Transaction synchronization across your nodes. That's also a difficult problem. Currently, we have like custom applications kind of that handle and can handle reorgs when they occur on the nodes. But this is a problem I think that is currently being worked on in a more blockchain-agnostic fashion. And so I hope next year at reInvent or at another conference we'll be able to present something specifically on this. If you replace your infrastructure every 30 days, how do you ensure your new infrastructure is at the highest block on startup? So that's where the snapshots actually come in, is we can tear down the old nodes. We have a snapshot that is recent. The new node comes up, and based off that snapshot, we sync down any blocks that might be missing. And as soon as we start passing health checks, then we put it into rotation behind the load balancer. Do you have something that does wallet synchronization for Bitcoin D variants for tracking transaction and unspent? I'm assuming it's unspent transaction outputs. Yes, we do. We have a custom application right now that sort of like handles this and tracks UTXOs across addresses that we care about, in the case of Bitcoin, that is. When blocks become out of sync because they receive different information at once, how do you get them back in sync? E.g., block 1 has data ABC, block 2 has data ABD. So this is hard. This event would be that two nodes just have different data, and they might, at some point, we know that they're going to correct themselves. When they correct themselves, that's what we call a reorg, or from one node's perspective, a reorg. So a new node says, oh, actually another block was introduced, and now that is the longest chain. That is the chain with the most work. I'm gonna consider that the longest chain. So actually, under the hood, the nodes kind of just handle that for us. How do you keep server-side wallets secure? Very good question. A lot of ways. We should probably, I think, give like a full talk into this topic specifically. I'm not going to go into too much detail on this now, actually. How do you handle version upgrade in your snapshot process? Binary download directly, PPA, pre-configured containers. Yeah, so we are code deployment solution. We can essentially click any single commit we want to, build the container required for that commit, and then deploy that. So when we build that container, that's pushed to a central container repository, and then when the new ASG comes online, it's going to pull down the most recent container and start that up. What is the lifetime of any given snapshots? So maximum length of time right now is 50 days. A lot of snapshots are actually torn down after about 3 days, though. How do you make sure transactions that you care about are the same across all Bitcoin nodes mempool for UTXOs? I'm not sure I understand what that question's getting at. We can essentially just, if somebody's sending funds into Coinbase, we don't necessarily credit their balance right away. Typically what you do is you wait for some number of confirmations. So you wait for some number of blocks to come in on top of the block that the transaction somebody sent in was included in. And at that point, we have pretty much probabilistic guarantee that the chain won't actually reorg around and undo the transaction that's sent into Coinbase. And so that way we have like a guarantee that we can credit their account balance. How does this snapshot selection engine cope with hard fork? Do you manually indicate to the engine about those concerns? Yeah, so we have like functionality in the engine where we can manually configure it to target a specific snapshot if we know something like a hard fork is happening. It's like a fairly flexible interface that we can use. All right, thank you guys. Cool.